Hello there, everybody. What's going on? My hair's a little sweaty. That actually gave a little away. Whoops. But welcome back to Discrete Math. I'm so happy to have all of you. How am I doing? I'm doing all right. Thanks for asking. Actually, weird thing in my life, you might have noticed that no one else is here actually talking to me. It's just me, which is, of course, what this is always like when you guys leave the Zoom lectures and me talking to myself in this room forever. I only exist in this space. But beyond that, it's because someone forgot to press the record button at the beginning of the lecture today. So during the live recording, well, I can't call it live recording because nothing actually recorded. The point is, I get to give this entire lecture again, which luckily I love math. So it's okay, I just love it so much. But anyway, so let's get to it and get to learning some discrete math. Today, we are finishing up our discussion on strong induction, or at least I hope we're finishing up. That's why I said a few hours ago, and we're finished. But anyway, so today we're talking about strong induction again. Let me get this straight going here. I'm trying to avoid this glare. I will figure this out. I have special lenses coming. But anyway, yes, we're talking about strong induction. And if I had the energy, I would write strong mathematical induction, but I think you guys know what's going on. This is strong induction. Let's just go over the idea of strong induction again. So before we get into it, just real quick. So the idea of strong induction is whenever proving a claim that goes like this. So you claim, so I'll say to prove that for all n and a set x and n such that x is greater than or equal to some a. So this is your set. This is just saying that x is a natural. This is a set of all natural numbers bigger than or equal to a. So everything a and above, right? So to prove that for all n in this set p of n by strong induction, it goes like this. So first you have a proof, and then you say proof by strong induction on n or whatever, and then you have your base cases right here, and your base cases, these are the oh, the lines are back. The lines are back. This is interesting. So you guys might notice some very faint lines coming to the screen. That's because the light is an LED. I think we talked about this last time. But anyway, I figured out how to fix it. It's just turn the light on and off, and it goes away. So anyway, so base cases, remember, when you're trying to prove these things, are your kind of beginning foundation of this domino chain reaction effect kind of thing. The way I like to think about it, well, actually, let me write it down first. So in the base cases, you'll prove that the first few of these are true. So you'll just straight up verify that PA is true, because it's everything above A, so you start with PA. So this will always be in a base case. And in weak induction, you'd stop there. There's only one base case. But in strong induction, there might be multiple base cases because it might end up requiring our inductive step, where we say that, oh, okay, if this claim works for everything up to n, it'll work for n plus 1. You'll see that in a second. Our inductive step to work might require a few previous cases, so we need some base cases backlogged to use in that first inductive step, and then that'll get us to the second one, the third one, or the fourth one, or the fifth one, the sixth one, go on and on and on and on and on. So anyway, so we'll prove P of A is true, and then we'll prove that like P of A plus 1 is true. And then you keep going, and eventually your last base case will be P of B is true. So P of B, so B is a number bigger than A, and it's the last thing that will prove, it's the last number will prove is true, follows P with the base case. So that's when we're to verify. Everything else, we're going to use the previous steps via the inductive step. So then after the base cases, you have, of course, the inductive step. And here, the inductive step, here's the part where you want to show that for all n greater than or equal to b, it's going to be your last base case. These are going to overlap. For all greater than or equal to b, P of A and P of A plus 1 all the way out to and P of B, or sorry, not P of B, P of N will imply P of N plus 1. So the whole idea here, right, is that the inductive step, you want to show that if everything up to N is true, then P of N plus 1 must also be true. That must also follow. And I really like to think about this as we've all been there, right? We were trying to like crank your old-timey 1920s car, and you got to get in front of it. You got to put the thing in, you got to crank it, right? The base cases are like your first few cranks when you do that. And eventually, after you crank the old-timey car, the engine will take over and that chain reaction starts. And that's what the inductive step is. So your base cases are the first few cranks to get you over the hump, to get you to the inductive step. And so the question, I guess, a lot of the times is, well, how do you know how many base cases you need? And it all comes down to how many previous steps you need to use in the inductive step. So I'll write that right here. So I'll say number of base cases needed is determined by how many previous cases the inductive step needs to prove the next step. And so we can see, actually, this is why in weak induction, we only have one base case. Because in weak induction, right, so instead of saying that all of these, the weak induction had, like, we don't assume that everything up to N is true. We just assume that P of N is true, and then show P of N plus 1. So in that case, we only need P of N to prove P of N plus 1. So the inductive step just needs one previous case, P of N, to prove the next case, P of N plus 1. So that's why we only need one base case. But there are plenty of proofs that we can think of, and we're going to do today, where the inductive step actually requires at least a couple, if not more, of the base cases, or sorry, at least a couple of the previous cases to prove the next case will hold. And so then you need a few of those base cases, your foundation, your first few cranks, and then the inductive step will take over. This will all make more sense with an example, but this is the idea. Prove your base cases, prove that everything up to N is true, then N plus 1 is true. That means then, well, then N plus 1 will be true because N plus 1 is bigger than N. First of all, that would prove B is true because this works for all N greater than or equal to B, and B is certainly greater than or equal to B. And so you can use this to prove that everything up to B is true. Well, then P of B plus 1 will be true. But we know everything up to B is true because of the base cases. So then you know everything up to B plus 1 is true, but B plus 1 is greater than or equal to N. So if this is in fact true, then you can use everything up to B plus 1 to prove that P of B plus 2 is true. This goes on and on and on and on and on. I feel like I am a broken record. So I'm just gonna move on. There we go. I'm just gonna move on broken records like all hipsters should.